Good morning or good afternoon, everyone, depending on where you are joining us from. Welcome to today's webinar. My name is Megan Franstein, and I'll be hosting the session today. And it's my absolute pleasure to welcome Dr. Loutjie Coetzee from Jaslovka here today. He will be presenting on the future of gold mining, AI metallurgy advancements. So just before we start, a few housekeeping rules or information. Please send your questions throughout the webinar. We'll allocate some time towards the end to address all of your questions. If it doesn't get answered today, we will answer it at a later stage via the webinar platform. For any related content on the webinar, please click on the widgets shown on your screen. And if you have any technical issues, there is a help icon that you can click on. So without further ado, let me introduce Dr. Loutjie Coetzee, who's our speaker. And Loutjie, welcome.
Yeah, thank you, Megan, and thank you everyone for joining this webinar. I really believe it will be an interesting insight into how Jaslovka is trying to, I think, really change gold mining, but then I think in longer term mining through better optimization using the power of AI. So my name is Loutjie Coetzee. I've done a PhD in advanced process control, and I've practiced that for most of my career for 16 years before joining Jaslovka to really look at optimization using the power of AI, which we'll dig in today. So just to give a bit of an overview, there's I think AI being a very hot topic in the general understanding, and people are quite excited about what this could mean, or can be very scared about what this can mean to their industry and their area of work. Is it going to be a good thing? Is it going to be a bad thing? Bad primarily in the terms of, is it going to affect jobs? But yeah, we can already see there's a lot of players in the game that's looking at all different aspects of mining and deploying artificial intelligence and machine learning to mining. So some of the areas, of course, that's having that we highlight here is exploration. And resource estimation. So AI algorithms are used to analyze geological data, identify the mineral deposits, and create a more accurate model for resource estimation. And the machine learning can help to predict where the richest ore deposits may be found. Drilling and blasting optimization, AI here helps optimize the drilling patterns and blasting techniques to minimize waste and improve efficiency. And advanced sensors and data analytics can determine the best blasting parameters for different geological conditions. Ore grade control. So AI models are used to monitor and control ore quality by analyzing data from sensors and cameras. And this helps to optimize ore blending and maintain a consistent quality during processing. Predictive maintenance is, of course, also a big one, where AI and machine learning algorithms are used to monitor the health and to try and predict failures before they happen. Predictive maintenance can therefore help to reduce downtime, extend equipment life, and, of course, save costs. Autonomous vehicles and machinery, where AI is used to automate the driving of trucks, the loaders, the drilling rigs, with minimal human intervention, and especially in hazardous environments. This helps to improve safety, but also increase productivity. And then minerals processing optimization, where AI can help minerals processing stage by analyzing data from flotation cells, crushers, and other processing units to maximize the recovery rates and reduce energy consumption. Now, this would be the area that we're going to be focusing on today. And then two other areas that's also very important is mine safety and hazard detection, where it's used to behavior. You can send out AI-powered drones to do safety inspections. Ventilation control, where for underground ventilation systems, adjusting the airflow. Also energy management across mining operations, environmental monitoring, etc. There's a lot of areas where there is AI being deployed and also being researched to deploy. But as I say, we're going to be focusing on mining processes today and how we can optimize that. Okay, for some reason, it doesn't want to change my slide.
I've changed the slide for you, Loki. Are you not seeing the new slide?
No, I'm not seeing it on my side, but okay, I'll let me just get a version on my side that I can use. Not sure why mine is not frozen. Okay, we want to set the stage here for what is the typical challenges that we're seeing in the mining space that we want to try and address with optimization. So just give me a second. So the typical ones that we identify is that there's infrequent optimization in a highly variable environment, and the environment is variable due to the ore that is changing, hardness, the type of ore that's mined, the blend of ore. There's a low response to these variability because there's a lot of manual work involved in doing process plant optimization, typically for the metallurgist. And this is due to the integration of lab and manual samples that needs to be reconciled with online data before you can do optimization work. Typically, metallurgists and other operating personnel is quite busy with what I call firefighting, where there's incidents or things happening on the plant that needs urgent attention, which then distract them from actually getting to the real optimization work. We also, in this industry, have a lot of turnover of operators and metallurgists, which means that institutional knowledge or that intuitive knowledge of how that specific process works doesn't get time to build up, or a new set of operators and metallurgists need to learn the process again. And during that time, you're losing efficiency during that learning curve. It's also difficult to track the performance of the process in near real time. And then coupled with the turnover of operators and metallurgists, it's ensuring best practice because, again, there's some nuance in operating a plant that to really get the best out of it. And if you have the high turnover, then the new guys coming in bring experience from a different plant, which might not be applicable and not necessarily best practice for that plant. Okay, can you move me to the next slide, please? Okay, now it's changing. So what is MetOptima? So it's for gold mines looking to improve productivity and or cost efficiency, where MetOptima has an advanced analytics suite that offers actionable data-backed insights for optimization. And we're really looking to optimize across the whole process from end to end. Next. So we call it an always-on AI metallurgists and operators. So as we say, the work of the metallurgist typically is to try and optimize the process, to offer the best economic performance, and the work stretches from front to back of the concentrator. And that's exactly what we trying to do with MetOptima, where it's doing this optimization, but just a lot more regularly and automated to assist the metallurgist. And then it gives the recommendations to the operator, and in that sense, assisting the operator and what is the best set points and conditions to set on the plant to achieve this optimal operating conditions. So we leverage AI and machine learning, and we'll dig a bit into what I mean by that a bit later. And we also have data analytics suite. So not everything will necessarily be in the form of recommendations. There's also other analytics that can surface important data to the operators and the metallurgists that can help them in decision making, where it's not a clear-cut recommendation that can be generated. Okay, so how does this work? So at a high level, MetOptima is a web-based system. So it's living in the cloud. I'm not sure if I have a highlight. Draw. Pen. Let me use a laser. I don't know if you can see my laser. Okay. Yeah, so there were the oranges. MetOptima is living in the cloud. And what we have is we have the process, and we have some instrumentation on the process that measure certain variables. And this is typically connected to some sort of PLC or DCS system, and that typically pushes data into a historian for posterity. And MetOptima then starts with an adapter here, where it then reads the data out of the historian and pushes this into the cloud database, all in a secure fashion. This data that's then in the cloud is used to train models that then model the process for us. And once the models are processed, the live data that we're reading gets pushed through the models to generate predictions. And using this, the system can make recommendations on how to operate a plant, and that is then pushed through a web interface for the operators and the metallurgists to digest. So the benefit is this can be available on-site and off-site for monitoring where people need it. So as we said, there's a number of data sources that we ingest that is typically online data sources will be connected to a PLC, DCS, but also we're looking at ingesting manual data sources that usually comes from the lab to give us a good combination of both online and offline sources in order to really have the full picture available for the plant. So the MetOptima interface is an intuitive web-based interface, which was designed with design thinking principles with the operators in mind. And really, I think the brains and the heart of this is the process models and optimization. So we're really collecting a large amount of data, as I say, both online and offline data sources that we can use to predict the behavior of the process, and then do a metallurgical and economic optimization to generate the recommendations. So the benefit of this is we it's really, we can now look at very highly nonlinear behavior of the process using the power of AI, and I'll expand on that a bit later again. But it's basically allowing us to capture this nonlinear behavior of these process plants. And also we can do a nonlinear optimization, which is economic optimization. As I say, all of this is hosted in the cloud, which is highly secure and highly available and we will make sure all of the data is handled very securely. So talking about security, here's just a snapshot of some of the things that we have built from the ground up into MetOptima to ensure that it is secure and safe. So all the data is encrypted, both in transit and at rest, so on the drive. We also segregate aspects of MetOptima internally so that if there's a breach on the one section, it's not exposing anything else. So the data, for example, is segmented further away from the interface with the internet. Also, there's role-based accesses, different internal firewalls, etc. So there's a lot of thought that's gone into how do we build this to be secure and safe to ensure our client data is secure and safe. So what we're saying here is we're trying to do system-level optimization. And I want to skip ahead to this one. So if we look at a typical control systems hierarchy, we have this pyramid that we talk about. That is our control hierarchy. So at the bottom we have the process. That's like the grinding mill. It's the actual sump. It's the pipes, etc. Same with the flotation cells and the leaching cells. Then on top of that, we have the actuators and the sensors. So that would be like pumps, auto valves, as well as densitometers, flow meters, level sensors, etc. So that is the first level of that, which feeds into the second layer, which is our base layer control. And the base layer control is where our PLC DCS typically lives, that have basic control loops, and we can do certain interlocks and safety systems there to ensure the plant operates. Then, in some cases, you will have advanced process control systems that will then look at usually a process unit, like a grinding circuit. If it's a very complex flotation circuit, the APC might even be split into multiple modules to deal with the complexity, and also leaching. So there will be multiple APCs, and they even in between grinding and flotation, or flotation and leaching, there can be thickeners and other process units that's not shown here, which might have their own APCs. And the benefit that APC brings, it doesn't just control the process to some standard set point. It can also do a matter of optimization depending on the type of APC that you have. So you can optimize the performance of the grinding or the performance of the flotation or the leaching to some extent. But typically these interfaces between grinding and flotation and leaching, and other process units that might be in between, is typically still left to the operators or the metallurgists to find out where should we be operating my flotation circuit so it's best for leaching, or where should I be operating my grinding in order to best meet flotation and leaching's needs. And that's where MetOptima comes in. It spans across all of these process units, and it fills in that gap that's typically still operated by metallurgists and operators. And this is also much more difficult. This is a lot more interactive. It's a highly dimensional system, a lot of inputs and outputs that you have to look at, and also very slow dynamics that's happening at this layer. So a change in the grinding circuit can take half a day or more to start affecting the leaching. The leaching itself has multiple days that it will take to operate. So, and then if you take recirculating loads through TSF into account, then you're starting to look at days worth of data later on. So it's very slow dynamics. It's highly dimensional. And it's also nonlinear in its interaction. So yeah, it's quite a complex problem, and it's the most complex problem that we typically leave to people to do to solve, and that's what we're trying to address with MetOptima. So maybe just to give an idea of the architecture. So if we have our basic flow sheet here, this is an example flow sheet where we have a SAG mill, open circuit SAG, closed circuit ball mill, that has a flash flotation feeding to a rougher. And so this is a very simple flotation circuit. Typically in gold, it's not that complex. We have the tails feeding to CIL tank 2. We have the concentrate going to a regrind and then feeding into CIL1, feeding into CIL2. So we have multiple paths for this, for the ore to move. And it's combining again, so we have to take into account how we split this, and also what the composition of the ore is, because that will affect how it's split between the tails and the regrind, so between oxides and sulfide ores. If there's a higher percentage of sulfides, it will affect how CIL performs, and if there's a higher percentage of oxides, it will affect also the CIL, and it will affect how we need to grind, both in the first stage grinding and the regrind. So we will typically build a high-dimensional model of the grinding circuit, flotation circuits, leaching circuits, and then connect it all together inside MetOptima, and let MetOptima then work out what should be the ideal operating conditions for grinding, flotation, and leaching as a whole to give us the overall best economic performance of the process, both in terms of production, but also to look at how we can do it in a cost-efficient manner. So yeah, we have, so just in terms of the data flow, we have the grinding, flotation, and leaching circuits. We have the sensor data that's in the historian. We push it through the different models. We're doing optimization, generating recommendations. And in this example, we might do it every 4 hours. So it means if it's an 8-hour shift, there will only be 2 recommendations in a shift. Why do we do it this slowly? It will depend on, of course, the dynamics of the process and the variability of the process. So that can be quicker after every 1 hour or as slow as 4 hours, depending on the variability. But the idea here is that, firstly, we're working with much slower dynamics. We typically will have an APC system under this that will ensure that you operating stably between these recommendations. And if you get a recommendation, you're moving to that recommendation and stay there. And so you need time for this process at a higher level to reach steady state and really operate there. So leaching being a much slower process, we're doing it every 12 hours. And yeah, even every 12 hours might not be enough time to reach steady state for leaching. So it can potentially be even slower if it needs to be. But the idea really is that it shouldn't provide a big load on the operators. That's why we want to make it slower, because they need to evaluate it and implement it. And if it's happening too frequently, that will create a big load on the operators. Yeah, so we're trying to minimize that. So yeah, I just want to take a bit of a segue before we continue. So I wanted to speak a bit on the AI and the power of AI and what we mean by that and why that is significant in this space. So as I said, I've done my PhD in advanced process control. So I've done basic process control, advanced process control technologies. And if we go back to the 1960s, around there, if you wanted to do multivariable control, so that means if there's more than one input and more than one output that you're trying to control at the same time for the same, to reach an objective, it was a very complex process. So here we just have a 2x2 system, and you can already see how complex this this system is. If I just highlight here, that is not a nice color. If I highlight this, this is the controller, and you can already see it's quite complex, just on a 2x2 basis. If we go to a grinding circuit, it can be a 7x5. If you go to flotation, you can suddenly look at a 20 by 5 type of system, which gets hugely complicated. If you now want to connect grinding and flotation, the dimensionality goes up even further. So doing it this way becomes almost impossible to do. It can be done with a lot of work, a lot of man hours, a lot of cost, but it is not the most efficient way of doing it. And you need very highly skilled engineers to develop this control system. And still, this control system will typically just give you regulatory control. It would just control to some set points that your operators or metallurgists need to set. So what happened next, the first revolution after this, in my mind, was the creation of model predictive control. So what this did is we now created a model of your process that modeled how does all these inputs and outputs behave in a dynamic fashion. And we send it through an optimization algorithm that then calculates the optimum control moves that we put into the process in order to achieve these targets that our operators and metallurgists are setting. So that was the first thing. The making a controller of 7x5 now becomes a lot simpler as long as you can model it. So the complexity of the control has become much less. As long as you have the models, the control is very simple to define in terms of constraints, in terms of trade-offs in terms of even running in bands. So you immediately had more capabilities with your MPC. You can do explicit constraint handling, which was much more difficult with a basic control, multivariable control systems, and you had guaranteed you can tune your controller much more aggressively while still making sure it will adhere to constraints. It can even deal with dead bands a lot easier. And these type of things you can tune on the fly very easily with advanced process control system or model-based type of advanced process control system. But you still had to get these models, and the models is now where the complexity has moved to, where originally it was the control control philosophy itself that was the challenge. Now the modeling has become the challenge in order to realize these controllers. And this is basically where we see the power of artificial intelligence and ML coming into play. So why artificial intelligence? So one of the machine learning is actually a subsection of artificial intelligence, and if I can summarize it maybe in a very naive way, what I see artificial intelligence is, it's if you're training, say, a neural network, but there's other network type or model types than neural networks. But let's just take neural networks because they're typically associated with AI. It's the big breakthrough is that deep neural networks, where you have a lot of parameters that you can train, allows us to capture basically a very complicated nonlinear function in our neural network. And the more parameters we can add, the more complex the behavior of this model can simulate, the more complex function it can start to represent. So if we think about the current state of the art, which is large language models like ChatGPT, etc., they basically billions of parameters that they are fitting. So the breakthrough is, how do we fit this billion parameter model to very highly nonlinear data in a way that it captures it accurately. And the machine learning techniques that allow this AI breakthroughs is basically what we're also exploiting. Because as I said, if you move from control to optimization, I think just before I've skipped a bit over that, so I just want to go back. One of the big benefits that model predictive control brought to the space is it's no longer just doing regulatory control, which means it's not just trying to control to a set point, but it can also calculate what is the optimum set point to operate at. So it's already doing optimization. But the challenge is it's based on the model and the scope of the model. And if our modeling is difficult, the scope that we have to reduce it to allows us only to look at the subsection of the process and optimize that subsection, which can be to the detriment of other sections. So, of course, you do get MPC scenarios where they cascade it and they can build models at a higher time scale. But yeah, it is getting quite difficult to do those models. So it is still the model complexity issue. So back to AI and ML, this breakthrough that's allowed us to see things like AlphaGo and, of course, the large language models. The big breakthrough behind it is basically being able to fit these highly nonlinear, high-dimensional models. And that is what, if we look at our gold processing plant from grinding through to leaching, it's a high-dimensional, nonlinear process. And the more information we can feed into this, the more of the dimensions of variability we can start to describe in these models. So that's why there's a lot of advanced instruments coming online these days, like analyzers such as the Blue Cube system that allows us to measure the composition of the ore that we're busy processing at different places in the process. So we know how the changes in the ore affects the behavior of the process. And the more we could fill in these gaps with these advanced instruments, and even making use of lab samples, because we're running at a lower time frame, we can build quite a descriptive model of how the process is going to behave under different conditions, and therefore allows the system to generate recommendations on how to operate it most effectively. But the challenges of applying AI and ML to the mining processes is firstly, which I haven't got on the slide, is that our industry is very conservative. If we look at like model predictive control, advanced process control, and advanced analyzers, we are far behind chemical process industry and petrochemical process industry. We have been much slower to adopt new technologies to drive efficiencies. So it's a conservative market. So we have to also be, in a sense, we want to push the envelope, but we have to be conservative and bring our customer along for the journey. So the next thing is, if we assume big data, which is the assumption behind a lot of the ML techniques, it doesn't fully hold because we have highly correlated process data. So yes, we have gigabytes and gigabytes of data, typically from a process, depending on the frequency that you're taking it. But the problem is the data is highly correlated. There isn't necessarily a lot more information in the large amount of data. So we actually need a lot of information to really do the modeling, not necessarily a lot of amount of data. If we look at other domains like social media and web and these type of things, the data is very uncorrelated. So there's a lot of information in the amount of data that is available. And therefore, you have a lot of information to train these highly nonlinear models. But we have to be a lot more careful when we're going to process data and mining process data, in that it's correlated and therefore doesn't contain as much information despite the high amount of data. Not all causes of change in the process are measurable, and that's specifically in the case in mining, where we don't necessarily have the instruments to online measure all the different variables. For example, something simple like you would think the mill density or the SAG mill density is not available as an online instrument. On most plants, the particle size for a grinding circuit is not available online. And that is like the main parameter of our grinding circuit that we can't measure, and so forth. There's a lot of things. We can't measure the concentrations of reagents in flotation, for example, to estimate what their effect is on the process. So there's still a lot of things that have an impact on our process which we are not measuring, and that's causing a challenge. Of course, there's dynamics in the data, and if we look at traditional AI and ML models, they're not specifically designed to deal with these correlated dynamics that come from processes, and that needs to be addressed in how you apply your AI and ML process. Domain knowledge is then key to understand also causation versus correlation. So I can't just say, okay, I have big data, I just throw that all in and I see what the model is going to give me. I still need to distinguish between causation and correlation because it is a process. You can find correlations which is inverse causation if you're not setting up your models correctly. So we can't get away that domain knowledge will remain key in applying artificial intelligence and machine learning correctly in the mining space. Process control principles of observability and controllability still apply. So this is not a magic bullet. If I can't see a certain variable, if it's not observable, that refers back to we're not measuring everything. And if it's not observable through indirect measurements, then the model's not going to capture that. It's not going to pick that up from the data. The same with controllability. I can't steer the process in a certain direction if I don't have the actuators to do it. So understanding process control principles is still going to be key in deploying this in the correct manner. And then another thing, because we are a conservative market, our clients still want to understand the thinking behind the recommendation. So they won't just be satisfied with, oh, just change your feed rate up or down, or change the water addition here up or down. They want to understand why we are recommending that. And we need to therefore do AI and machine learning in a way that we maintain this transparency and this interpretability of what is the thinking behind the system, to build the confidence that it's doing something that is metallurgically sound, according to first principles. So we're not really looking at creating new knowledge yet with the AI. That definitely can happen, but to a large extent, the processes are well understood, and therefore what the models recommend and how they recommend should match up with our understanding of metallurgical principles. And of course, there's a lot of hype, as I say, at the moment in AI and ML that can do very fancy things. And I definitely think that it is changing the world already, and it's going to continue to change the world. But our focus has been on, we need to conservatively apply this, and we need to apply it in a way that produces real monetary value to our clients. So we're not going to go after flashy things just to make it look cool. We are looking strictly at where does it make sense? How can we do it responsibly given these challenges? How can we do it in a conservative way, but still pushing the envelope and really deliver on the bottom line? And that's what our clients are interested in. So back from my segue is then, what type of benefits can we expect in terms of gold processing plants? So we are quite confident that we can see something between a 5 and 7% increase in throughput if the process is not mine limited, of course. If it's mine limited, then we can't really do anything about it on the process side. And looking at the recovery improvements between 1 and 3%, depending on how efficiently it's currently running, and really exploiting that inefficiencies between process units. Of course, we want to do this in a way that reduces costs, or at least relatively, if there's more production, the cost goes up, hopefully less than the increased production. And it allows us to really track closer to real time how well is the process doing. So just having that information available in itself can be quite valuable to our clients. So the additional benefits is, as we said, if we look back to operator metallurgist turnover, is how can we operate the plant in a consistent manner between shifts with a turnover and operator or metallurgist that the process still responds efficiently. And that's what MetOptima allows, because it will rigorously calculate these recommendations based on sound models of how the process really work, and consistently respond to disturbances in a predictable way. So it also gives automated documentation that can be used for employee education. So we can see it if they rejected certain recommendations, and we can ask them why they rejected it, and use that as a training opportunity to say, okay, but this is what the system wanted to do in this scenario, and this is how it would have played out. Then that helps to build confidence, and it also helps to improve the employee's understanding and get to that best practice that we're trying to achieve. Of course, there's also the continuous improvement that can be happening, because now if the process is operating effectively, other inefficiencies might start to become apparent in the process that the metallurgist and the production team can look at to say, okay, how do we debottleneck these areas is now becoming clear impediments to production, and rather focus their efforts on that debottlenecking. And of course, we have this impact tracking to make sure the process remains sustained in its performance. And of course, part of the efficiency improvements is to reduce the consumable costs, because we don't have to overdose on cyanide, for example, just to make sure that we're getting the recoveries. We can run closer to to the optimum values. We can also, if you look at the grinding mill, if we're operating it more efficiently, your steel consumption, both in liners and ball, can be reduced. And of course, energy consumption in the grinding mill can also be reduced, at least a specific energy, when you're operating closer to optimum. Okay, so in summary, as we said at the start, we have the challenge that there's infrequent optimization in a highly variable environment. So how do we try and address this with MetOptima? We're giving frequent set point recommendations every few hours that helps to reduce the variability and respond to the variability, therefore improving the throughput and the consistency of your process. We say there's a low response speed due to manual work because you have to integrate manual lab and measurements and analysis. And MetOptima helps automate this process by integrating data from online and manual sources into a rigorous optimization model to improve the response time. So efficient use of time due to firefighting instead of optimizing the performance. We are reducing the workload necessary for the metallurgist by automating a lot of this work, and therefore also hopefully if the processes run more efficiently, there will be less fires to put out, and they can focus on looking at debottlenecking the process to further improve optimization. So high turnover of metallurgists and operators, and which causes difficulty to ensure best practice. The recommendations, as we said, is done in a rigorous model and will be done irrespective of day shift, night shift, what operators are on duty. And by giving feedback to them on recommendations they didn't understand, the operators are learning the best practice for that specific plant that they can also apply and really track that the system is doing its job correctly. So I say difficulty tracking performance and managing variability and change. So we can do continuous improvement through real-time impact tracking. So we can see, okay, yes, we are improving, but there is still room for improvement. Where's the areas for improvement? And I say the automatic documentation helps to understand if this is due to operators rejecting recommendations due to lack of understanding, that they can really engage in that training of the operators and improve their understanding. Or if there is really something wrong with the system, that a model update is necessary, that can also be the case, and that can also lead to a continuous improvement. So it can work both ways. So yeah, I think that comes to the end of my presentation. So I think there is some questions that has been put on the Q&A.
Yes, thank you very much, Dr. Coetzee, for that very insightful presentation. And we do have quite a few questions in the chat. Just a reminder, if you still have something you'd like to ask Dr. Coetzee, please place it in the Ask a Question section at the bottom of your screen. So the first one is from Neo Shaka. He says, hi, Loki, just a question. Is MetOptima specifically for gold, or can it be used for other commodities? What makes it only applicable to gold and not other? Because so far it looks like it can be used for other minerals as well.
So the short answer is it can be applicable to other processes. It's more a historical question that Draslovka's primary business as being a cyanide supplier, and also the recent technology of the glycine leaching technology has both been a gold-only application, and therefore we focused on gold as our first application. But yes, the technology itself is broadly applicable in other commodities as well.
Great, thank you. And we have a question from Hattie. Is AI optimization centered around industrial mining only, or for alluvial mining as well?
I think it's for now industrial mining. So yeah, it will, again, we'll have to understand the changes in the process and how we can apply it and what is available in terms of automation to really see how applicable it is, because we still depend a lot on base layers of control systems and instrumentation that allows us to operate. But there is a certain measure of online available instrumentation availability necessary for this.
Okay, fantastic. Next one is from Nuretin. How about data safety of OT, software, historian, etc.? If AI gets data from OT and or connected to IT?
Yes, so what happens is there's a very small module that will run locally on the OT network connected to the historian, and it only can make an outward connection. So the firewalls on the site is set up that no inward connections to the OT network is possible at all. Only an outward connection is allowed from this module, pushing the data in an encrypted fashion to MetOptima. As there's at the moment no control actions being pushed back by the system, it's not necessary for the system to write any data back into the OT network from the internet. So that eliminates the threat of somebody hijacking that connection and having nefarious interaction with your OT network.
Great question. Next one is from Rodrigo. What is the minimum volume of production to use the process?
I don't think it's really a minimum volume that's necessary to use it. It's just your value, what you will see in terms of nominal numbers will be bigger, the bigger the volume is that you're using, of course. So if we're looking at the typical gold plant, what those type of numbers that we've presented represent is conservatively easily $10 to $20 million a year of value that's generated. But if you have a significantly smaller plant, then the value might go down to $1 million a year. So it's just a matter of how much it will be worth in absolute terms to you. But in terms of the system being usable, there's no limitation.
Okay, fantastic. Victor asks, is AI applicable to exploration of copper, porphyry copper?
In terms of exploration, I don't know, because we're not working in the space of exploration. But there's definitely companies that's using AI for exploration purposes.
Yes. Okay. Great. We will be sharing this recording. The recording will be sent from the event platform after the event, so you'll still have access to it afterwards. Nuretin asked another question: is there a sample mine increased OEE or recovery or EBITDA?
Yes, we have a trial plants that we are busy with, and one where we already seen a recovery improvement. We're still ongoing, so I'm not going to disclose anything more, but it's already aligning with our expectations, and we're getting more of that example sites that we will definitely make public as soon as we're at that point.
Artura asks, what AI or machine learning models do you use?
That I'm not going to answer because I don't want to give away too much of what we are doing and how we are doing it.
But quite a variety of models are used. It's a suite of different models.
Yes, there's also models for different aspects, and as part of the secret sauce to some extent.
Yeah, great. Nicole asks, does MetOptima integrate with all PLCs, example, Cytect, Vigeo?
As long as they have OPC connections, we can integrate with any system.
Good. Question from Yannick. How many days do you usually need to develop an AI or machine learning model applicable to copper and cobalt's hydrometallurgical plant?
Yeah, so given that we're still in the early stages, we see the project of taking around 6 months to develop the models. So first it will go through a phase where we evaluate, are we going to be able to provide value? So we call it the diagnostic phase. We look at your historical data. We look at what is the opportunities. Does it make sense for both parties, Kraslovka and the client, to continue with AI application. And if we both say yes, it looks like there's enough value, then we'll get into the modeling and testing and deploying. So it still takes quite a bit of time and man hours to do it at this point in time, but we hope to reduce it in future down to a 3-month period. But for the moment, I would say it's a 6-month period at least.
Great. Question from Neil. Very nice, Loki. Thank you. Are you currently giving all recommendations in advisory mode to mates and operators, or is it tied in a cascade mode to the MPC?
No, it's only in recommendations to the operators and the metallurgists. Again, it's to build trust in AI systems. As I say, we have a conservative market, so we're doing it intentionally. I'm sure at some point, if the clients become confident in the recommendations and the reliability of it, they would request it to be automatically connected to the MPC system. But that's not where we're starting for now. We're first starting in this mode of recommendations only.
Okay, great. Question from Bob. Is this a replacement for my APC?
No. So yes or no, depending on what APC you have. Personally, if it's a model-based APC, I would say it's complementary to your APC, because we can cascade on top of the APC very easily. The MPC it's well known how it will operate under different conditions. If it's a fuzzy logic-based APC, I would not try and work with that for a few reasons. The main one is that fuzzy logic systems are usually designed to try and mimic the best operator. So it's difficult to interpret how these fuzzy logic systems are going to behave, and they might not always behave well with dynamics. Similar type of challenge that AI can have is if they're not dynamic aware, they need to make decisions based on steady state, and if you not reach steady state properly, they might not give the best results. And they're already trying to do optimization potentially across different process units. So you will have competing behavior from a fuzzy logic system and MetOptima. So if it's fuzzy logic or expert system based, I would say yes. In that case, I would rather replace it with a model based APC with MetOptima. But if it's already got a model based APC, then I'd say it's complementary.
Cool. Question from William. How much historical data does a plant need to have before MetOptima can be used?
Sorry, just repeat that.
How much historical data does the plant need to have before they could use MetOptima?
At the moment, we're saying 2 years worth of data would be good. If that's not available, we can still do a diagnostic on less data. So as I say, it comes back to the problem of information versus the amount of data. We need variability in the process that's generating our information. So the more historical data we're looking at, the more variability we have of the process, and therefore more information we have to model off. So if there's been a high variability in a short amount of time, then potentially we can do it in a shorter amount of time. But my short answer would be 2 years worth of data.
Okay. Another question is, a major challenge for some large-scale mining operations is the increase in clay and insolubles. Do you see any alternatives to mitigate the problem that this creates in production?
Yeah, this is a much more a process challenge than it is necessarily a process control challenge. I've seen it at one of our clients where the clays have caused problems with screens blocking and therefore production or lack of throughput. So yeah, one potential option would be to blend it with something that has less clays. That's just a clay. But again, you will now be milling something and processing something that is not valuable. So that's a lot more of a process question. You can, in the specific cases and understanding that, can probably see if you can mitigate it to some extent with a control optimization solution, but it might very well require a process change to deal with it properly.
Okay, question from John. Does this take over the responsibilities of my metallurgists and operators?
At this time, no, and I don't think even in the long term, no. So we specifically looking at it as an assistant. Sorry, just give me a second. We're seeing it as an assistant to look at a specific area of responsibility for operators and metallurgists, which they don't always have the time to do rigorously, and we're assisting them in that case. But there's still a lot of functions metallurgists and operators are going to do which falls outside of the scope of MetOptima, and therefore it will not be a replacement for them.
Okay. Question from Timothy. Since we can't write back to the process due to security concerns, how would you use this for actual control as opposed to guidance?
In that case, we will have to start writing back, and a secure solution will have to be developed. So at the moment, we're not looking at that because it's not the target for us. But in future, when we do want to write back, we'll have to develop a secure mechanism of pushing that recommendations to the PLC or DCS system.
Okay. Another question from Jack is, does the plant need to be stable before we can use MetOptima?
No, we're trying to develop it in a way that it helps to stabilize, because we're looking at the whole process from front to back. And so, for example, we don't want to push too much material into the flotation circuit that can make the valves of your flotation circuit run at maximum, and therefore you lose level control. So it will, because it knows the effect of grinding on flotation and leaching, we can come up with recommendations that will help you still get good performance, but without pushing the system too hard to the point of instability.
A question from Jacques. Are recommendations generally followed, or how often do operators accept the system's new suggestions?
Yes, so it has been followed, and of course, part of it, of improving that is, as we say, the client needs to understand, the operator needs to understand what is behind the thinking behind the recommendation, that it actually makes sense and will improve the process. And that way we're getting better adoption from the client. So it's a part of a training and coaching, and that's partly why it's also taking long. We're dedicating almost 3 months of this process of adoption just to make sure people really understand and change management is done, and that they have confidence in the recommendations and actually adopt it.
Great. Question from Lacey is, do we need any additional IT infrastructure for this to work?
As long as the mine has an internet connection and firewall infrastructure that allows us to connect from the OT network and push the data into the internet, and also display the web interface at the plant, then no additional IT infrastructure will be required.
Okay. Another question from Greg is, does this only work for specific flow sheets?
No, so I think it connects with the other one about commodities. It's not specific to any specific flow sheet, because there can even be gold mines that doesn't have flotation at all, or gold mines that has multi-commodity, so gold, copper. You can therefore have other flows in your flotation there, a more complex flotation. It connects up with the other commodities, so it's infinitely customizable. It just takes time to model all the different processes, and at the moment it's quite I think still a human resource intensive process, because as I highlighted earlier, we need to do it in a way that makes sense, that takes the process dynamics into account, that takes the challenges of process process dynamics that I've already mentioned, but to take all of those challenges into account in a conservative way that will actually provide benefit and not give you negative results.
Perfect. Thank you. That is all the time that we have, all the questions that we have time for. So thank you everyone for attending, and a reminder to the audience, you can still submit your questions on the platform. They will be answered via the platform at a later stage. And thank you, Dr. Coetzee, for this presentation, and we've really enjoyed hearing more about AI and gold mining. To the attendees, you will receive an email from the event platform just giving you details of how to access this on demand. So thank you for joining us, and we look forward to seeing you next time.
Yeah, thank you very much from my side as well. Enjoy your afternoon.